Well, we've touched a lot on quantum mechanics, and I know you have some reservations about relativity as well. I've never quite understood what they were. Maybe.
Well, it's the same question. You see, first of all, insofar as relativity takes this space-time continuum, then it implies that time is like a substance or something you move through, and I don't think that makes sense, you see. Now, there are a lot of ways in which you can see that relativity and quantum theory need to be changed together. Now, see, if we come to quantum mechanics, and I say one of the things about quantum mechanics is that there are two very elementary points that it doesn't deal with, you see. One is the existence of things. See, quantum mechanics says nothing can be discussed except what will be observed when you have a piece of equipment, the probability of that. Now, if we take the whole universe, we would have to suppose another universe of observing equipment, perhaps quite a bit bigger than the first one, before we could see what that meant. Nevertheless, we must say that in some sense this does not require that universe of equipment. It's there without it. You see, so the first step, it's something like Bohr saying the classical mechanics didn't explain that atoms are there. You see, that was the most fundamental thing, the clue to something new. Now, see, the quantum mechanics doesn't explain that matter is there without really a tremendous amount of equipment to specify its state. Now, suppose I say now that, first of all, though, coming back, the things are there without the equipment somehow. And the second point is quantum mechanics doesn't discuss the actual process. You see, if you take a radium atom, say a single radium atom decaying into a Geiger counter with the gas in the Geiger counter, then quantum mechanics says it has a wave function, and in 2,000 years half the wave function leaks out of the atom. But in some cases something happens immediately, and in fact you can discover, let's say it takes 10 years to decay. So what happens is, if the counter doesn't work for the first 10 years, you know that nothing has happened, that the wave function is entirely inside for the first 10 or 100 years, or whatever. Right? And that contradicts the idea of Schrödinger's equation, which says that it was leaking out all the time. You see, so something is happening whose movement is not described by Schrödinger's equation. Now, the theory says Schrödinger's equation is the most complete possible description. So I say that must be wrong. That Schrödinger's equation is an abstraction of a fragment.
But at one time you tried to look at this through the notion of hidden variables.
Well, that's one way of saying that there's more to it through hidden variables. But now that was perhaps too classical. It was merely a way of getting insight into...
But would it be true to say that there was some misinterpretation of what you were trying to do there?
Yeah, I think people thought I was trying to return to classical concepts, but I was merely using the hidden variables to get imaginative insight into what the theory meant. So one could see that the hidden variables would have certain peculiar properties which suggested that you should look at it in another way. Now, you see, for example, one discovers that these hidden variables have the property that they imply instantaneous connection of all parts of the universe, an extreme form of wholeness, and some people have said, well, that's so strange that we don't want to consider it. Now, I don't think that makes sense, that attitude, because you say, as long as we do the computation, we can we don't imagine anything about it, so, you see, we're not disturbed by anything that happens. You see, we have all this happening, all the correlations of things far away from each other. We say it doesn't disturb us because we never mention it, we only compute. So, therefore, I don't understand the attitude which says that if we use hidden variables, they have strange properties, and therefore we would rather not use them. See, I'm saying by using hidden variables, your attention is focused on these strange properties, and you begin to see that quantum mechanics, by understanding it imaginatively, even if perhaps not in a fundamental way, you see that quantum mechanics implies something very new, which you are missing by just doing the computations.
But then the sort of traditional physicists would ask you to produce a new prediction or some new
well, I
features.
think that again is a sign of a certain attitude to physics, which says the essential point about physics is to predict something, you see. And I say, why do you want to predict? You see, the people talk about prediction so much that you almost feel there's a predictive instinct that will be satisfied if you can predict. But obviously that's not the case. The reason why people want to predict is to confirm that their ideas are on the right track. Now, I'm trying to say that in some cases you can't predict, and some of the things are ambiguous, you see.
But would it have been true to say that if you had, with the aid of hidden variables, predicted something, which was in contradiction to quantum mechanics, and in fact the experiment agreed with your prediction, it would have been very difficult to retain conventional quantum mechanics.
That's right, but we're confronted with the situation in which the traditional way of trying to see the weakness of a theory is inadequate. You see, the traditional scientific method is to say, wait until an experiment clearly shows you that you're wrong. But if you're going on with confused methods, no experiment will clearly show you're wrong, because you can always modify the theory, as people have done, with all sorts of modifications. Now, so I'm saying we've got to look at it differently and say there is something which the present theory does not have in it, which requires understanding. Namely, there is an individual actual event, this decay of the radioactive nucleus, which is simply not accounted for in the present theory, and we must put in new concepts to account for it and see what happens. Now, you see, I think there's a lot of confusion here, because first of all, many people don't fully and deeply realize that there is something missing. They get so used to doing statistical calculations and saying only statistics matters that they don't notice there is an individual actual fact which is not accounted for. Now, if something is happening that's not accounted for, you want to put something into your concepts that accounts for it, you see. Now, even if you can't use it to predict anything more for the moment. I mean, now, perhaps later you will predict something, but I think there's an overemphasis on prediction and on getting results, which is stifling physics, you see. That step of Roger Bacon, which made experiment important, was so creative in that time, is now getting in the way because it is being held on too rigidly. At present, we don't want to emphasize predicting particular results too much, but rather trying to give an account and get some order into the fact, in the whole fact, you see. I feel the fact is not fully accounted for in an orderly way. Since it's confused, if we start with a confused account of the fact, we will never get a clear clue for the next step. Now, I think this confusion ties together between relativity and quantum theory. See, quantum theory does not give a clear account of the fact that atoms exist, really everything exists without too much intervention by human physicists, and that furthermore that actual processes take place not described by Schrödinger's equation at all. Now, suppose we would begin with another account, simply to say that stationary states, the world is very nearly in a stationary state, you see, but it's with some transitions. And we say stationary states just simply exist. That's our way of talking, and they make jumps from one to the other. And we haven't explained why that happens, but we're only accounting for this fact. And therefore, then we don't need this equipment at all. We see, we're not going to interpret quantum mechanics as what an observer will see, but as a process of jumping between quasi-stationary states. Now, and then we now explain that we have what we call a material system, which comes by a stationary state of a large number of atoms, which, when you solve the many-body wave equation of quantum mechanics, you see that you cannot make this relativistic at present. You see, you need to put one common time for the whole system. Now, this material system is essential to relativity, though, because if you take the theory of relativity, it always presupposes some quasi-rigid material system, which is the frame to make your observations from. You see, I don't think that from a single atom you could ever get any definite meaning to relativity. You wouldn't have a clear definition of properties such as direction, for example, and so on.
But could I ask you the sort of thing Penrose was doing, in which he tried to take collections of atoms, and he thought in that way you could define notions of direction.
I understand that's a particular approach, but I think he still accepts the rest of the quantum mechanics, which implies that there's the observer who will observe these things.
Yes.
And therefore I feel that there's no clear, unconfused account of the actual fact in front of us. You see, I want to start by saying the physics has given us some facts, but they are not clearly, the actual language of discussing these facts is confused.
Yes.
Now, he is working on some particular mathematical structure to try to do something which may well be worth doing, but I'm trying to discuss something else.
Yes.
I think something has to go on which is still a lower level, as it were.
Yes.
Now, so I'm saying we have got to consider that this piece of apparatus, this block of matter exists, you see, without any help of observers. It's in a very nearly stationary state, and it determines a frame. And when you look at relativity theory, you see that's one of the chief things that's missing, is that one sees no clear definition of a frame. See, if it were not for quantum mechanics that makes matter stable, there would be nothing in relativity that would allow for the frame that measures anything.
Yes.
So there seems to be a deep relation of relativity and quantum theory.
Yes.
Now, you can pursue this because you also discover that if you take the stationary states in one frame and then move the system and accelerate it, the stationary states of that system are not compatible with those of the first. See, they are non-stationary, and they correspond to operators, which we discussed before, are not compatible. So if you have one system in stationary states, then another system moving by is not in a stationary state.
This is moving uniformly.
Uniformly or non-uniformly. Yes. It's not in a stationary state, but relative to the first system, but it is relative in its own frame.
Yes.
So if there were an observer inside, he would be built out of atoms in those stationary states, then he would see everything relative to those stationary states, changing. Yes. So we now see we have an interesting conception, which is that there's a relativity of stationary states, and that what is stationary for one block of matter is not stationary for another. You see, now that concept is missing. That removes the difficulty about the fact that you give the same time to all the atoms in one system, because we say there actually is a common time which is relevant for determining the stationary states of the first particle in technical terms as the time displacement operator for that system. Another system has another time displacement operator, determines another set of states. The two systems are not stationary together. Now, we can now get an extension of relativity because we've introduced a new concept, which I call the concept of the material frame, and of the natural frame for the stationary state. Now, this means, however, that Schrödinger's equation cannot be taken as a complete account anymore, because each system has its own Schrödinger's equation in its own giving its own stationary states, you see, and one should not try to say that Schrödinger's equation, a single Schrödinger's equation, covers the whole universe.
Yes.
So we say a particular material frame, a block of matter, for example, is determined by solving Schrödinger's equation for some atoms.
Yes.
And then that can be extended abstractly into the surrounding space, but then another set of atoms has its own frame, and they may be related approximately, but not exactly. You see,
yes, and how does the notion of space, is the notion of space as a relational?
Yes, well,
notion?
Space comes out as relational space and time, because, you see, from this structure of atoms we imply a certain space, you see. Now, therefore, every particular block of matter has its space, which is extended abstractly into the surrounding region, and all these different spaces interpenetrate to form what I call a multiplex. You see, there's many spaces folded together.
Yes.
I say, therefore, rather than thinking of space as a single substance, we can think of it as an abstract relations of the multiplex. Now, each multiplex each element of it being a fragment that is based on one piece of matter.
Yes. So it's the space we think of as three-dimensional is really a multiplex of many interpenetrating spaces. Yes. See, and that's an order that we are imposing on space and relating it to matter.